Okay, so our next speaker is Professor Somnath Basu from ISR Kolkata, and he will be speaking on dichotomy and Poincare duality. So over to you, Somnath.
Okay, thank you, Surajit. So yeah, so this is the last talk for my part of the lecture series. So I thought I should talk about certain things which people have classically studied using the things we have talked about in the first three lectures, meaning various computational applications of rational homotopy groups. And I also thought to connect it with Poincare duality, which you have seen in several talks, in Samik's talks and also in the previous talk by Pranav. And hopefully at the end it will connect up with something which is more along the lines of algebra, but we'll see. Okay. Okay. So I want to begin by recalling this dichotomy called rational ellipticity versus rational hyperbolicity. So what does it say? So I'm going to assume, if I do not specify otherwise, that all the spaces we are considering are going to be simply connected and they'll have finite rational cohomology. So that means the Betti numbers are all finite and the sum of the Betti numbers is also finite. Okay. So most examples that you encounter in the realm of manifolds and so on are of this type anyway. So this is an assumption that we're going to make to make the statements cleaner uh, and the explanations simpler. Okay. So given a space which has this finite rational cohomology, you can define an integer n to be the dimension. This is not the usual dimension, but just think of it as a formal dimension if you want, or an algebraic dimension. It is the maximum integer n such that the nth cohomology of x with rational coefficients is non-zero. All right. So for instance, if your x was S1 cross R, then only the first cohomology is non-zero, the second cohomology is 0. So the dimension would be 1. So you call this the dimension of the space X. Okay. And of course, for closed manifolds, this n turns out to be equal to the dimension of m as a manifold. So they agree on the realm of manifolds. Okay. Okay. So here's the definition. So we're going to break up space as described above into two types of spaces. So, and how do you define that in mathematics? Well, you define one type and then you say whatever is not of this type is of the other type. So we're going to do precisely that. So a space X is called rationally elliptic if you look at the rational homotopy groups, which is what this does. Now this becomes a vector space over Q. You take its dimension and you add all the dimensions up. So you say a space is rational elliptic if the sum of the dimension of the rational homotopy groups is finite. Okay. So in particular, this says that the rational homotopy groups will be 0 after a certain index j. Okay. And if this does not happen for the space X, then you call the space rationally hyperbolic. Okay. So it's a pretty simple enough definition. We'll soon see what this entails. Okay. So first, some examples. Since we talked about spheres and complex projective spaces already using minimal models, you know that these are rational elliptic because the odd spheres only have essentially one non-zero homotopy group in dimension n. I mean, when you tensor with Q, and the even spheres have two in dimension n and dimension 2n minus 1. And complex projective spaces also have two because they are at the base of a circle fibration where the total space is an odd sphere. Okay, so these are rational elliptic spaces. One can show, in fact, we did talk about this a little bit, that Lie groups and more generally homogeneous spaces, spaces of the form G mod H, the G is a Lie group and H is a closed subgroup. So these spaces are also rationally elliptic, meaning take the rational homotopy groups, compute the dimension, add them all up, that's finite. Okay. You can even use the long exact sequence and the tensor with Q and so on to show that if you have a fibration F E to B, where F is a fiber, and B and F are rational elliptic, then E is also going to be rational elliptic. Okay? Because rational elliptic means that the rational homotopy groups of B and A will vanish after a point. But then by the exactness, the rational homotopy group of E will also vanish, beyond that range. Okay, so yeah, so these are three sort of classes of examples. More generally, if you are looking for examples in the context of manifolds, then it turns out one can say a lot more, but I'll just specifically restrict to 4 manifolds because this is probably the first that people try to the first the class of manifolds that people try to study, because once you have a simply connected 4 manifold, it is determined pretty much by the intersection form at the level of H2. And you already saw the intersection pairing as a non-degenerate pairing due to Poincare duality. So H2 sort of, along with the intersection pairing, in some sense determines the 4 manifold. So the statement here is that such a 4 manifold is rationally elliptic if and only if the second Betti number is at most 2. So if the second Betti number happens to be 3 or more, the 4 manifold will necessarily be rationally hyperbolic, meaning this sum is going to be infinite, okay? Which in particular means that you are expected to see a lot of, you're expected to see infinitely many Qs in the rational homotopy groups of such a manifold, right? Okay, so, okay, so these are the examples. So now I want to talk about the dichotomy. So this is just by definition. So what does it mean to say something is rationally elliptic apart from this definition? And what does it mean to say something is rationally hyperbolic apart from how it's defined? Okay. So this is dichotomy theorem 1. So here I'm going to talk about the rational hyperbolic case first. And the next one I'm going to talk about is the elliptic case. Okay. So again, let X be a rationally hyperbolic space of dimension n. Recall dimension n means it's the maximum integer n such that the nth cohomology of X with Q coefficients is non-zero. And rationally hyperbolic means that the sum of the dimension of the rational homotopy groups is infinite. So then it turns out there's a whole host of sort of things one can conclude. Sorry. But I'll just, so if you want, you can have a look at either of the books, either the original like rational homotopy theory by Felix, Halperin and Thomas, or the one algebraic models in geometry. They talk about even more properties and then other applications of this. I'll just list the one which I thought would be relevant to see for the first time. So being rationally hyperbolic actually implies something much stronger. It's saying that if you look at this sum, we of course know that the sum as j runs from 2 to infinity is infinity. But it's saying something much more. It's saying that this partial sums, you take j running from 2 to m and then add this up. And this has exponential growth in terms of m. So what does it mean? What does it mean to say a sequence of exponential growth? So you just call this number am. It means there exists a positive constant lambda and a constant c bigger than 1 such that for m sufficiently large, this number am is bigger than or equal to lambda into c to the m. So that's what I mean by it has exponential growth. So, or at least it has at least exponential growth. It could grow even faster, but this is bigger than or equal to, this could grow even faster. Okay. Yeah. So you actually have a growth rate which is at least exponential. So it's not just it's going to infinity, it's going to infinity at a very fast rate. The second condition says that, I mean, the second sort of, I shouldn't say condition, the second assertion is that there are no large gaps. So although you have this growth, you might say, are there large gaps in the sequence? Meaning, are you guaranteed that there is no large sequence of integers j, j plus 1, j plus 2, dot, dot, up to j plus k, so that all the rational homotopy groups are 0? And the answer is no. So what this means is, given any k, if I look at the rational homotopy groups from pi k to pi k plus n, there is going to be some L in between k and k plus n such that the Lth rational homotopy group is non-zero. So you do not have large gaps in the sequence, meaning you do not have large number of sequences of 0 rational homotopy groups for such a space. Okay. Okay, so if you want to connect this up with what we talked about in the last slide, I said if you take a 4 manifold with the second Betti number to be, let's say, 3, you would expect it to be rationally hyperbolic. I mean, that's a fact. One can check it in several ways, but that in particular would mean that you would expect lots and lots of non-zero rational homotopy groups to appear. But we know that the generators of the rational homotopy groups as vector spaces are dual to the minimal models, right? So if I'm trying to construct a minimal model for a given manifold, I would be able to recover this fact in some sense, although it gets very hard to compute. So if you think of this 4 manifold, take CP2 and then take CP2, connect some CP2, connect some CP2. And so if you try to write down a model for this, well, this is a 4 manifold, and it basically has the second Betti number 3, because each CP2 has a line inside it, a complex line, so it contributes 1 Z for each of the CP1s inside the CP2s. So you basically need 3 generators in degree 2, and they're closed. X1, X2, X3, dxi is equal to 0. Those correspond to the dual of the fundamental class of the P1 inside here, the P1 inside here, and the P1 inside here. But and so of course you have to also put a y in degree 3, okay, such that, so you have to put several things in degree 3. So what is this capturing? This is capturing that, so if it was just CP2, the generator of, the cohomology class corresponding to P1 squares to the top thing, right? Because that sort of is the top cohomology, right? So right. So here the point is that because of this connect sum business, one knows, I'll just skip this. If you write down a minimal model and you have seen it, you'll be able to figure it out, that you have to basically introduce certain generators in degree 3 to kill certain things because of the cohomology ring structure of this space. And so you have to introduce 4 such things. But then you sort of realize, once you introduce U to kill off X1, X2, V to kill off X2, X3, and W to kill off X1, X3, and Y to kill off the sum, you realize that your job is not done. You have to add more generators. Why? Because if you look at this formal element, X1V minus X3U, this is now a closed element. Because if I take D of this, D of X1 is 0. And then I get X1 into D of V, which is X2, X3, minus X3 into D of U, which is exactly X3, X1, X2, which is X1, X2, X3, because these are in even degrees. So that is 0. But you see, this is an element of degree, which is of degree 5, right? Because X1 is of degree 2 and V is of degree 3. But there is no cohomology element of, there's no cocycle of degree 5 in here. This is 4 manifold. So you have to kill this thing. And so you have to kill any such new closed generator that appears, any new closed element that appears by this construction. I have to keep killing them as you move higher and higher up to construct a minimal model. So at that point, it sort of becomes an algorithmic process, but you have to kill them nonetheless. And that is one explanation for why you need a lot of generators in the minimal model, even beyond the dimension, for this kind of thing, which hopefully explains why you expect this to be rationally hyperbolic. Okay. But anyway, this is just a quick glimpse of how you do the computation, but computing this by hand would be pretty tedious at best. Okay, so the next theorem that I want to talk about is again called Dichotomy Theorem 2, and this is going to be about the other kind of spaces, namely rational elliptic spaces. And again, this is of dimension n, meaning the nth rational cohomology is non-zero, and beyond that, all jth cohomologies are 0. Right? So here, the first property is that the rational homotopy groups actually vanish beyond 2n minus 1. So beyond j equal to 2n minus 1, which basically means that pi j of x tensor q is 0 whenever j is 2n or higher. So this is somehow like is being captured by this formal dimension. Okay? And here's the second point, and I'll say a lot more about this subsequently. I've already seen what Poincare duality is earlier, as well as in Pranav's talk, who phrased it exactly in the way that I would probably need. But anyway, so it turns out that for such a space, the rational cohomology ring satisfies what's called Poincare duality. In other words, there's a non-degenerate pairing from hk to hn minus k, and so that's what I mean. But I'll say more about this anyway. And the third thing, so again, in the elliptic case, there's a whole host of things you can talk about. I've just chosen a few because my aim is not to go into a detailed discussion of what happens when it's elliptic versus what happens when it's hyperbolic. I just wanted to point out certain things you can deduce, and then these will have a lot of computational applications. So the third one is the total dimension, which means you take the rational cohomology of X in every degree, calculate the dimension, and then add them up, right? So we know that this is finite because of our assumption on the original space X, but it actually is bounded by 2 to the n, where n is the formal dimension of X. Okay. Okay. So actually, you have already seen that this thing is actually strict because you can take X to be one of the even spheres, in which case for an even sphere, you do have pi n of like pi, how should I say, pi n of Sn tensor Q is Q, and pi 2n minus 1 of Sn tensor Q is also Q if n is even, and otherwise it's 0. So you cannot really lower it down to anything smaller. And if you take the example of the torus, for example, the torus is not simply connected, but it's a simple space. So even then you can compute that the dimension is 2 to the n, the total dimension. So yeah, so as I said, there are further constraints that are imposed on X algebraic topologically, if you assume it to be rationally elliptic. And I strongly urge you to read one of the books where they talk about this in detail. But the point is that these constraints basically impose so much of conditions on X that rational elliptic spaces are very few and far in between in a certain sense. So if you were taking a generic sort of simply connected space or manifolds, you would expect them to be of the other kind. Namely, you expect them to be rationally hyperbolic and not rationally elliptic. And you already saw that in the case of a simply connected four manifolds. Okay. So yeah, so to explain condition 2, at least formally, let me talk about Poincare duality algebras and then Poincare duality models, which would again tie us back to the minimal model setup that we have been talking about. And then I'll come back to Poincare duality again after talking about this and some examples. Okay. So are there any questions so far? Okay. So, right. So I'll be working in the setup of CDGAs. Okay. So here right now, I'm not assuming there's a differential. So this is just a CGA. So a commutative graded algebra A, everything is over Q. Some of the things I am talking about here can be done over arbitrary fields of any characteristic. I might mention them if I remember to do so as and when I state the results. But for the most part, I'm interested in things over Q just to keep it coherent and in tune with the other lectures. So a commutative graded algebra A over Q is a Poincare duality algebra of dimension n if a couple of things happen. So I expect each of these, so I am talking about A to be these, I mean, there's supposed to be sort of cohomology of spaces and things like that. So it's indexed upward. So A is a direct sum of A to the j, and each aj is of finite dimension as a vector space over Q. I also want an to be one dimensional over Q, where, so when I say dimension n, this is what I mean. And I want everything beyond n to be 0. Okay, that's the first thing. And there's a multiplication because A is an algebra. And so I want this multiplication to induce a non-degenerate bilinear pairing. Okay, from AJ tensor AN minus J to AN. So AN here is basically a copy of Q, and I want this to induce a non-degenerate bilinear pairing. So as Pranav remarked, I mean, this basically means that you'd be saying that this thing is sort of the dual of this thing, because everything is finite dimensional now. So AN minus J it can be identified with the dual of AJ. Okay. So this is what a Poincare duality algebra is for me. And I want to talk about CDGAs, which if you ignore the D, the underlying thing is a Poincare duality algebra, and it's connected to a minimal model. So those are the kind of things we want to talk about. Okay. But this is pretty straightforward definition, and I've seen this many times. So so the first example that should come to your mind is if you take a closed simply connected manifold and take its rational cohomology ring, then its rational cohomology ring is a Poincare duality algebra simply by Poincare duality, right? Okay, so that you have seen in earlier talks. Yeah, so I want to talk about Poincare duality models. So what are these? So I'm going to restrict myself first to simply connected uh, closed manifolds. So here, remember that for such a space, the dimension is the same as the formal dimension. They're both n. So a Poincare duality model for such a space is first of all going to be a Poincare duality algebra, but it has a differential. So it's going to be a Poincare duality algebra A of dimension n with a differential d, such that I have first two quasi-isomorphisms, and this is something very commonplace in these kind of discussions, that you do not have a direct map, but you have a zigzag. So you have MM to be the minimal model of M, and you want a quasi-isomorphism from the minimal model to this Poincare duality algebra, and we know that this minimal model is, there's a map to the, the APL of M, which was as defined following Sullivan's work. So we want this AD to have to inherit a map from the minimal model, which is a quasi-isomorphism. Okay, so effectively this AD, when you compute the cohomology, will compute the usual cohomology of M, the rational cohomology of M. Okay? That is sort of the point. And I'll also assume that A0 is Q and A1 is 0. So A1 is 0 is the analog of saying that the space is simply connected. So these are also often called connected, I think simply connected DGS. And A0 being Q means connected. So I'm going to make this assumption here. Okay. Okay. So again, if you ask, okay, what are some examples? And it's always good to have examples along the way, even if these are the same examples that I keep repeating. But it's good because these examples are easy and also highlight certain things which will help me introduce them without further introduction. So again, let's go back to spheres. So if you look at spheres, if you look at the odd spheres, for example, the minimal model, remember, was a free graded commutative algebra on one generator in odd degree, and the differential was 0. And so this is basically a q in degree 0 and x and q span by x in degree k, where k is odd, and that's it. But this was effectively the same as the cohomology ring of the sphere itself, right? And this is clearly a Poincare duality algebra, right? Because you just don't have to do anything. You're just saying Q tensor Q to Q is a non-degenerate bilinear, pairing, but it is. So for odd spheres, the minimal model is itself a Poincare duality model. There's nothing to check. What about even spheres? Well, for even spheres also, one could take the cohomology ring of the even sphere. So take A comma A to be the cohomology ring, and as we remarked earlier, the cohomology ring is already a Poincare duality algebra, and you take the differential to be 0 because on the cohomology there's no differential. We've already taken the kernel mod image, and then it's pretty clear that there is a map from the minimal model to this thing. Now recall the minimal model was you have a free graded commutative algebra generated by x in degree 2k and y in degree 4k minus 1. So that dy is in degree 4k, and then this is simply x squared because x squared is 0 in the degree 4k cohomology of S2k. So you have to kill x squared by introducing y. So this was the minimal model, and what would the map be? The map would simply be you send x to any choice of a volume form on S2k, or like a rational volume form, and you send y to 0, right? And that would and that is going to be a quasi-isomorphism. Okay, so the point being that even for the odd sphere, you could have said that instead of saying the minimal model is the Poincare duality model, you could have said I just take the cohomology of the odd sphere, and then the minimal model gets naturally identified to the cohomology because they are pretty much the same thing. So in both cases, I do have Poincare duality models. Okay. Are there any questions? All right. So let me sorry, talk about yeah. So if I want to sort of enlarge my class of examples, I could always talk about products. And so if I have two manifolds M and N with Poincare duality models, which I'll call them AMDM and ANDN, then what do you have to do to say that M cross N, the Cartesian product, is a Poincare duality model? I have to produce a map from the minimal model to to some Poincare duality algebra. And so what we do is we just look at this sequence of zigzags. Okay. So first of all, the minimal model of M tensor the minimal model of N. So all of these have their own differentials. I've just ignored them because it was getting too long. It's clear what the differential here is, right? It's D tensor 1 plus 1 tensor D. And you know how to apply it as you move elements over each other by the Koszul rule. Similarly, the differential here is dm tensor 1 plus 1 tensor dn. So there is a quasi-isomorphism from this to this, because the minimal model is quasi-isomorphic to M and this is quasi-isomorphic to AN. So you have a quasi-isomorphism here. But note that there is also a quasi-isomorphism here, which is simply tensoring things, right? So now and this is something we did talk about. This is almost like the analog of pulling back forms and then integrating and so on. So there is an actual quasi-isomorphism from the PL models of M tensor PL model of N to the PL model of M cross N, the piecewise polynomial Q forms with Q coefficient. So we had talked about this if you look at my notes earlier. So we now do have a map. So we have this minimal model, and this basically will be quasi-isomorphic to this. This is a minimal algebra, and this is also quasi-isomorphic to this. And one can check that this is a Poincare duality algebra as well. Okay. So M cross N admits a Poincare duality model. Okay. So Lie groups, again, I'll bring them, I keep bringing them back because they're probably, in some sense, the simplest from this perspective, but then they might be of independent interest to others because it lives in so many different intersecting fields. So the point was, like odd spheres, the minimal model can itself be taken to be the Poincare duality model, because you can take the minimal model for the Lie group to be the free graded commutative algebra generated by finitely many odd elements, right? So then that is practically the cohomology. So okay, so right. So in view of Hoff's result, the cohomology of G with Q coefficients is a free commutative graded algebra on finitely many odd generators. So that is what we talked about earlier. So it's just that. So the point is that you can, in all three of these cases, the Lie groups, the spheres, and so on, you saw that you can simply take the cohomology of M with Q coefficients, take the differential to be 0, and that is a Poincare duality algebra. I mean, it is a Poincare duality algebra for any simply connected manifold that we already talked about, but it also served as a Poincare duality model for these examples, for spheres and Lie groups. And that is not by accident, okay? And so I want to talk about that en route to talking about Poincare duality further. So yeah, so in all the examples, we could choose the cohomology ring as a Poincare duality model, and there's a reason for that. So that leads me to what is called formality, and I would like to talk a little bit about that, and then continue with talking about Poincare duality, and then hopefully connect it with certain things you have seen in algebra, and hopefully you will see again in algebra. Okay, so are there any questions? Okay, so yeah, okay. Yeah, so, so I want to talk a little bit about formality. So what do I mean by formality? So here it means something very specific. And one could probably say a lot about these things, but I'll stick to the context at hand. So a simply connected space X will be called formal if there exists a quasi-isomorphism from the minimal model of X to the cohomology ring of the rational cohomology ring of the space, which can be thought of as a CDGA, where you simply put the differential to be 0. So it's just your old CGA, commutative graded algebra. Okay. Okay. So whenever such a thing happens, you call such a space formal, and we've already seen examples of this. Spheres are formal, complex projective spaces are formal, Lie groups are formal. Okay. So we can actually have a counterpart definition of this in the context of algebras, and they're actually in some sense the same. So given a CDGA A comma D, excuse me, I'm going to call A comma D formal if there exist quasi-isomorphisms of the following form. So each of these are CDGAs. So I have A comma D here. I have this over here. So given A comma D, I can take its cohomology, and then I can think of this as a CDGA where I simply put the differential to be 0. So I'll say A comma D is formal if there's a zigzag of quasi-isomorphisms connecting AD with its cohomology ring. So, I mean, so this is just a notation. You have seen these zigzags earlier also in Pranav's talk. So the point is there should be maps here and then maps here. So they may not expect one single map, but whenever this thing happens, you call A comma D to be formal. Okay, and you see the connection between these two definitions, that if I had a space, then I would basically want to put APL here, the piecewise polynomial forms with Q coefficients of the space, and then I have the cohomology of that, but the cohomology of that is nothing but the cohomology of the space, correct? But now I have a minimal model for the APL, so I can put the minimal model here, and in general, whatever these CDJs are, I can actually have minimal models for these if they're one connected. And then because maps between minimal models, when they're quasi-isomorphisms or actually isomorphisms, they can be inverted. So this definition essentially for spaces boils down to this particular simplified definition. But these two are equivalent in that sense, that this is the more general definition. But if you're dealing with A to be APL of X, then because of the properties of minimal models, it boils down to this, because you can replace these by their minimal models, and then there's one single map from one minimal model to here, which is the usual definition of minimal model, and to this one. Okay. Okay. So everything here is over Q. Okay. So again, what are examples of formal spaces? Spheres are formal. Complex projective spaces are formal. Although I didn't do that computation, but it's pretty similar. Lie groups are formal. And if you take products of formal spaces, they are going to be formal. And if you take retracts of formal spaces, they're also formal. So some of these are actually proven. I mean, it's not too hard to check these, but they're proven as examples in the book Algebraic Models in Geometry, if you like concrete examples. Okay, and there are other things people have proved, but one of the celebrated results was that complex scalar manifolds are formal, and this is a result due to Deligne, Griffiths, Morgan, and Sullivan. So in fact, what they prove is that complex scalar manifolds are formal over R, meaning they do everything with CDGs over R. And then there's a result of Sullivan, which says something which is formal over R is also formal over Q. So that's why they recover this notion of formality from there. Okay. Okay. So yeah, so in other words, the examples we saw earlier, where we're trying to construct this Poincare duality model by simply taking the cohomology ring, was basically due to the fact that those examples were of formal spaces. So you could have essentially assumed the existence of such a map, but we simply constructed them without knowing that they're formal. So in any case, so that is the point of connecting it through this. Okay. Okay. So yeah, so now I want to talk a little bit about existence, and existence meaning not the existence of formal objects. I mean, they all exist obviously, but existence of Poincare duality models. So this is, I'll definitely not be able to prove it, but the point is that if you have a minimal model of a very special kind, namely it's free graded commutative algebra on V, and then you have a D, and suppose V only consists of odd degree pieces. So V is a direct sum of V3, V5, V7, but no even pieces, right? suppose that dimension of V is finite, then you can check that this is a Poincare algebra because you only need this to be a Poincare algebra, and then it's pretty clear that this is a Poincare algebra because like none of the odd generators will repeat because of the graded commutativity. So if your minimal model is of a very special kind, then this is already a Poincare algebra. So in Lie groups, this indeed happens. The model is of this kind. Okay. So of course, one worked on certain examples, and then Halperin, this was probably almost 35 years back, conjectured that Poincare duality algebra models should exist for simply connected manifolds. And so probably I think 15 years ago, Lambrechts and Stanley proved this theorem, where they proved that every compact simply connected manifold admits a Poincare duality model. Okay. In fact, they prove it in the context of CDGAs and so on in the algebraic setting, and then applying that to APL, you get this thing. So the original result of Lambrechts and Stanley is CDGAs over fields of arbitrary characteristic K, not just over Q. And then if you take K to be Q and apply it to the CDGA that you get by APL of M, where M is this given manifold, then you recover this theorem. Yeah. So if you want to have a look at the construction, you can sort of have a look at it. So it's it's there. So the point is, in the context of Poincare duality, you can define something called a Poincare space or a Poincare complex. And what is it going to be? Well, like you saw in Pranav's talk, you can talk about things at the level of integers and equalities, or at the level of pairings, or you can enlarge it to some sort of things about other, like this categorification thing. But you could also be sort of naive at the same time and say that, okay, I forget all the chains, co-chains business, and I simply define a Poincare space to be something which mimics this property that happens for a manifold, meaning that in a closed oriented manifold, I have the fundamental class M. And then the fundamental class M, basically, when I cap with the fundamental class M, I get a map from, from cohomology to homology. And that should be an isomorphism, and there's a shift in degree, right? So that we already know. So the cap product with the fundamental class induces an isomorphism. So we want exactly that to happen in the context of a general space without caring whether there's something deeper underlying. And so the definition is going to be a space X of topological dimension n. So in our case, the examples are going to be X is going to be a CW complex or a subcomplex of some Euclidean space. So the dimension n is just the usual dimension of the highest dimension of the cell, right? So given such a space X of dimension n, we want it to be equipped with some element which I'm suggestively denoting as bracket X, in order to keep reminding you that for manifolds, this is the fundamental class in the nth homology of X, such that the cap product with this class is going to give you an isomorphism from the kth homology of X to the n minus kth homology, because kth cohomology of X, sorry, to the n minus kth homology of X. Okay. This is definitely true in the manifold setting. You have seen it. So this is going to be a definition of a Poincare space. Okay. So right. So with this in mind, let me talk a little bit about what's called the Spivak fiber. At least this is the notation Felix, Halperin, and Thomas uses, and then hopefully it will connect to something algebraic at the end. Okay. So what you do is imagine yourself inside Rn plus k. So this is just a large enough Euclidean space, and you have yourself, a subcomplex X of dimension n. So it's a finite n-dimensional subcomplex. Okay. So it's a CW complex of having cells of dimension at most n, and it's a finite, meaning it has finitely many cells in each dimension. This is inside Rn plus k. And so for the most part in the computations, in the applications, we assume that k is sufficiently large, maybe bigger than n plus 1 or something like that. But the point is, given this X inside Rn plus k, you take n to be a regular neighborhood of X. So you can think of n to be a small enough tubular neighborhood which deformation retracts to X, something along those lines. So if n is a regular neighborhood of X, you can denote by delta n the boundary of this neighborhood, right? So for example, if X is a sphere inside some Rn plus 1, you can embed it inside an higher Rn plus k by simply adding extra copies of R. That's basically like stabilization. And then you take the boundary. So the boundary is going to look like the original sphere cross a disk of the complementary dimension, right? So the point is, this is also something Samik had mentioned in his talk, that usually when you're studying problems of this kind, the properties of X are also tied up with how this is embedded inside the Euclidean space. But in a sort of stable sense, it doesn't really matter what how this is embedded if you know that stably up to homotopy they are isotopic. So which is true for finite CW complexes. So we just, for the discussion, assume K is sufficiently large. So now if you look at this boundary N, you look at the inclusion of boundary N inside N itself. So this is a map, but this is not a fibration. But you have seen this also quite explicitly in Pranav's talk, that you can talk about the homotopy fiber of this map, meaning you basically replace this by basically a collection of paths sort of starting here and ending in N, and then the homotopy fiber is going to be the collection of paths starting on boundary of N, and paths are entirely in N but ending in a fixed in a chosen point in N. So that would be the homotopy fiber of this inclusion, right? And so you define that to be the Spivak fiber, and is denoted by F subscript X. So I'll do an example in a moment. Hopefully that will give you a picture of what's going on for those who are not too comfortable with homotopy fibers, but you've already seen this in quite detail in Pranav's talk. So yeah, so the point is, because these any two embeddings are going to be isotopic after stabilizing, they're going to be the same for K sufficiently large on both sides. So up to suspension, this thing defines a homotopy invariant of X, this space F of X. Okay. So if I take this simplest example, consider the standard embedding of S2 inside R3. So this is the usual unit sphere in R3. You can then stabilize it further by thinking of R3 as R sitting inside R3 cross 0, which sits inside R3 cross 0 cross 0, and then you can keep stacking zeros at the right end. And you can think of S2 sitting inside RK plus 2. But then the point is, if you think of the neighborhood N to be as described here, such a neighborhood of S2 inside RK plus 2 is simply going to look like S2 cross DK, right? Because the tubular neighborhood of S2 inside R3 itself looks like S2 cross D1. And now you're simply adding more and more copies of this thing. So it looks like S2 cross DK. And so the boundary is going to look like S2 cross the boundary of DK. Okay. So now if you try to compute this homotopy fiber, what are you looking at? So if you go by the definition, FS2 is simply going to be all paths in N starting at a point in the boundary. So here V stands for a unit vector, and it should end at a prescribed point P0, 0, right? Okay. But you notice that if I look at this map has two components, right? Because N itself splits into a product. So gamma has two components. The first one is gamma 1, which goes from P to P0. And the second one is gamma 2, which goes from V to 0. But for any gamma, the second map, gamma 2, is just a map from a unit vector in Sk minus 1 to 0. But the collection of such paths can always be homotopy to give you the standard radial map from V to 0. Right? So you can always deform the second component to the radial path joining V to 0. So effectively what I'm saying is you can deformation retract Fs2 down to a collection of paths from P to P0, and in the second coordinate you have a standard path going from V to 0 by the map 1 minus T into V. So once you fix the second path as the radial path, then basically that's determined by this point V, right? And in the first component you have all paths joining P to P0, where P0 is fixed and P is allowed to vary over over this S2, right? So what you realize is that this homotopy fiber, or the Spivak fiber, is homotopy equivalent to the path space of S2 based at P0 cross Sk minus 1. This corresponds to the choice of V. The path space is contractible, so this corresponds to, this is homotopy equivalent to Sk minus 1. Okay. This is a simple example, but the point is this can be vastly sort of generalized, and this is exactly what Spivak proved in his thesis. So he proved that fx is a homotopy sphere if and only if x is a Poincare complex. So if you start off with this x to be a Poincare complex or a Poincare space, then this Spivak fiber is a homotopy sphere. Okay? And this is just a simple instance of that. Okay, so this once we have this set up, this will help me connect with the last few things that I want to talk about. So if there are no other questions, allow me to move on to the next slide. Okay. So excuse me. So yeah, I want to finish by talking about Gorenstein spaces, and this is something you have seen an analog of this in Shrikant's talk already, where he talked about Gorenstein ring, and so this is exactly going to be related to that. So before I say what it is, let me continue with what we are doing, right? So you look at the reduced homology of fx. In the case where x is a Poincare space, the reduced homology of fx is concentrated in degree k minus 1 because it was sk minus 1 in the example. In general, it's a homology sphere. It's a homotopy sphere. So the reduced homology only has uh, uh, 1q in some degree, and then so the dimension is 1. Correct. But in general, it turns out the reduced homology of fx can be computed through things you have already seen on the algebraic side of the lectures using derived functors called x and so on. So here's a fact which is not too hard to prove if you have seen these functors and how to compute certain things using those functors. It's a short sort of lemma in so this is basically following a paper by Felix Halperin and Thomas. Uh, so so they prove that for a simply connected complex x, if you are trying to compute the reduced homology, that's what this tilde denotes, of the Spivak fiber with respect to k, where k okay, I mean k is a field. If you want to put k to be q, but you can take k to be any field. And this turns out to be equal to calculating the x groups over the over the cochains of x with k coefficients of these two things. So this is the cochains of x, but there's a shift, and you've already seen this shift appear again in Shrikant's talk, and then this k is basically just k. So one way of computing this would be you have to resolve this k as a free c dot x module, and then you have to take the home, and then you have to compute the x groups. Okay. The point is this: the reduced homology can be computed by computing the x group of this, both as modules over the cochains. Okay. So in particular, in our case, what we have x to be a Poincare complex or a Poincare space, and fx is a homotopy sphere. Whenever fx is a homotopy sphere and it is simply connected, this is concentrated in some degree, and that is just a copy of q or k, which means if I am calculating the total dimension of the x groups, that should be 1. So we conclude that the dimension of x c dot x of k comma c dot x is 1. So this is dimension calculated over k, of course. Okay, and this is something you have seen. So let me take this moment to remind you where you have seen this. You have seen this in Shrikant's talk precisely, where he defined a Gorenstein ring to be something which was defined like that. So it was in the context of local algebras. So if you go back and compare that definition with exactly what we deduce here, we can now define the following. We can say that a Gorenstein space, but this is at k because your k could be varying. It could be q, it could be some other field. So we'll say x is a Gorenstein space at k, or a k Gorenstein space if it's a simply connected space. And this, the total dimension of the x groups are 1, which means in some dimension you will get x of one x group to be k, the other ones are all 0. So that explains also this shift. So explicitly this says where you will get this to be the non-zero group. Okay. So yeah, so and in particular from what we talked about, Poincare spaces or Poincare complexes are examples of Gorenstein spaces. But a priori, a Gorenstein space need not have a Spivak fiber. but you can still talk about these things. So I think this is a good place to end. Hopefully, Shrikant may talk a little bit about these things in his last lecture. I don't know.
Yeah, I'm planning to do that. Yeah.
But yeah, so I think this is a good place for me to stop. So I'll stop here. Okay.